Oh, then let's start. We have here exactly half hour. No question, please. A lot of topic. What we are talking today. Today we're talking about reverse engineering and Intel PT processor trace feature. Why it's important, and it's probably a new tool for you. It will be not the only reverse engineering tool you will use in the future, but it's an add-on to your tool suite. And I will introduce this because it's a really powerful tool where other tools you use will not work. Today we will talk about flow control, and what you see here on the picture is somehow the forwarding path. So if you create source code or have source code and compile this somehow, this is the flow control path which you can create with CLang. But this is the forwarding path. Reverse engineering, we talk about the reverse part. So we have the machine code and go back to disassembly and then going back to even decompile things. For the agenda, for the next couple of minutes, we'll talk about flow control, why it's important, and this section is about to level up and get everything on the boat, what we are talking about, to get some, same ideas, what we are talking about. Then we talk about the Intel processor trace, what it is, and then third is how we can use it from Linux. We talk about perf, and then how you can really use it for your reverse engineering as a task. And then some practical tips and also some shortcomings that will not work with Intel PT. So now the first section, what we are talking about. We are talking about flow control. And if we are talking about flow control, we talk about static analysis and dynamic one. The static is you have the binary somehow, then you use your tools. We will talk about later of this. And then you get into the things, but without really executing things. You're building the flow control graph, look how things will work, get a rough idea what you have on the executable or library in front of you. Dynamic flow control is the opposite somehow. You're running the code, execute things, how it behaves somehow. And normally, if you're doing a reverse engineering, you will use both techniques somehow. The one focus more on the dynamic aspect, so it's really a personal experience somehow. But normally, you will do this in this way somehow. And for all of this, one aspect is really important. This is the concept of the basic block. The previous talk was about JavaScript and email and things like that. Now, if you close your eyes, please think about all the time on assembly, right? So this is what this talking is about. So if a function is there, you have a function prologue, then you have this conditions, if-else things, branches, and then you have a function epilogue where you return to the callee somehow. Please keep this in mind. And the basic block is a block in the assembly. If it's started, it executes all the instruction there and branches out at the end somehow. But if it's executed, all the subsequent instructions are always executed or retired by your CPU as a one atomic block somehow. This is a concept not only in the reverse engineering or control flow, it's also important for compiler optimization and even for the hardware itself somehow. We'll talk about control flow and control flow graphs. This is what's locally to one function. So if they have branches, else branches, statements somewhere within. This is, and if you build this control flow graph, this is the thing what happens in one function. The call graph is something what you call, as you call functions. This is the call graph. If you're a Retera 2 user, for example, you use you stick to the function, and for the control flow graph, you are typing A for analyzing, G for graph and F for flow, and then you get this control flow graph. You see it later. And you get, for the call graph, you are calling A, G, C to get a local call graph, and capitalized G, C for the overall call graph somehow. So this is built in all the reverse engineering tools, and you can use. On the right-hand side, we see just instruction there, disassembled for the text block. And this is what we are talking about. This is, if you're reverse engineering, it's all about instruction and get a feeling how it works. So I said static and dynamic control flow analysis. The static one is you look at the graphs there, created with Radar 2 on the right-hand side, and get an idea what's happening there and get things done, or if there is some anti-debugging technique, how to patch things there and get a rough idea how things work. And what you're doing there is you understand the program logic, you identify key things or obfuscating. This is what you're doing there. On the opposite, the dynamic flow control, you're really executing things, retiring things, and the great thing is about this, then if you're analyzing some malware, you really see what happens there, right? And the static control flow graph generation gives you everything, but it's really important what is really executed, and the static analysis can be really complicated in some cases, and you don't get the runtime aspect somehow. And this is what you get with the dynamic flow control if you really run things. So you saw it in text here on the right-hand side, the indirect jumps and things like that. It's really hard and tough to get it, what's happened there with static analysis. So you use both methods, and for the dynamic flow analysis, you use debugging tools, right? So GDB is the most powerful debugger somehow, but there are some other debuggers built in the reverse engineering tool, like, for example, Radar and things like that. But that's not the only one to do dynamic flow control. You can also use a unicorn, for example, to execute just some, not emulate the whole operating system, emulating just an architecture, for example. So you have a lot of tools there. On the right-hand side, you just see a GDB and a graphical front end, for example, to get things done. So, but if you're doing a dynamic analysis, it's not that clear. You have a lot of complexity in doing there. You had code obfuscating, right? You have anti-debugging technology built in. So if a debugger is running, the malware checks if there's a debugger running. It checks if there are ptrace call, say something, no, I'm already attached somehow, and the malware exited somehow, and don't execute the things they want to do. They try really hard if it's executed in a virtual environment and things like that. So really hard to get all the debuggers and dynamic tools running to doing malware analysis. So this was the introduction somehow. And now we switch over to Intel PT. What is Intel PT? Intel PT is a hardware feature introduced with Broadwell CPU. So it's really Intel features, not implemented on AMD x86 processors. And it's somehow think about as every execution, every instruction is somehow snapshotted. But this is not really as it works. At the end, you will see what it's happened. What it's really done with Intel PT is all the I wrote control flow influencing instruction are recorded. So if it's sending call, this is recorded. And remember from the introduction, the basic block where an instruction is somehow started, all the subsequent instructions are always executed. There's no need to record this instruction. It is really required to record only the instruction that had influencing effects, like branches. And this is the instructions or the results of the instruction that are recorded. Think about if you have for a current processor, which executes or retire 4 billion instructions every second. If you really record everything, it's a lot of data, and this is not how things will work. So this Intel PT just records the minimum what is required to reconstruct things. And then later on the decoding side, it will really decode things that are executed. We will see it later. Intel PT is really resource efficient. So the overhead is just, if you can measure things take the overhead, take the time if you execute with and without Intel PT, it's just 2 to 15%, depending on the workload. So is it CPU intensive? It takes some more overhead, but it's really not measurable. This is also important for the malware analysts who do some timing analysis, to detect if there is an or debugging there. The influence is not there. This is why this is really great. The Intel PT, it's not visible from the application side itself. Like if it's debugger, you can do some things, but Intel PT is nearly not detectable. So this is a great advantage there. You have a lot of volume for what you record. Sure, it's a lot of things that are still recorded, and it's supported on all the processors, the Intel processors since Broadwell. How is this done? Just to get an idea, every time something is executed, a call, a function call, and so-called packet is recorded in memory, really efficient. And this is done in the kernel somehow. The kernel manages everything, and later on you see all these packets. And there are a lot of packets that Intel PT supports somehow. So a call is a dedicated packet that's recorded, and also branches. It's all about branches in the processor somehow. There is just 1 bit. So if there's a branch, think about if else somehow. Just if it's taken or it's not taken, is encoded as 1 bit into a meta packet there. And the meta packet, it's called TNT, taken, not taken. Somehow it's just really 1 bit is recorded. So you see it's really efficient how things are done and implemented there. But there are a lot of other packets as well to do timing measures in an efficient way. There is, the power modes are detected and recorded somehow. Also the P states, the processor, how fast the processor spins somehow, it's recorded, and everything is somehow recorded. It's required to do some analysis. So this is how things are done in the processor. And let's see here an example. You see it on the left-hand side. You see just a small main function, and there is in the middle. It's a little bit small, but probably you should see it. There's an if-else statement, and it adds a counter or increments or decrements the counter there. And you see on the upper side, it's just with object dump the function, the main function disassembled. On the lower side, so you see redirect to the flow graph generated. So you see the function prolog, then the if-else branch, and the function epilog. And what you see on the right-hand side is really what the Intel processor trace records. You really see the recorded things, and you see the PT write. This is some marker you can add to your code. Here, this is some marker you can add with result in some instruction and record it if you enable things, and you see it here. And within that, you see just a taken or not taken packet there. So it's here. It's an N, so it's not taken, and this is just how this recording. Nothing more. It's really required to reconstruct the function. It's just the call to the main. This is recorded before. This is the function pointer to main. And here only the not taken is recorded. And this is everything what's required to reconstruct everything there. And you see a lot of things happening there. I just highlighted we are on line 8893 here already. So a lot of packets and Intel PT packets are recorded already, because a lot of things happened before main, right? So the dynamic loader kicks in, the glibc kicks in, and everything, loading the dynamic, everything happens here. So really a lot of things is recorded, and you can reconstruct nearly everything based on this. Now we see how Intel PT works, how we can use it. And from Linux, there's Perf, a tool not really introduced 15 years back, don't remember correctly, introduced by Ingo Mollner and Thomas Gleixner. This is so the framework for performance things. It's an in-kernel framework, it's a system call, and it's a user space tool. And from this subsystem, you can use Intel PT. For record things, you just type a perf record. Say you want to use Intel PT and the workload. So you can record a whole CPU, you can record all the CPUs, or you can limit to a user space application and only use in the user space and not in the kernel space as well. So just check the man page for details. Here it's important that you're limiting what you want to record and not record too much. Now that we know how to record, the decoding comes into play, because now we have record these Intel packets somehow, but how we can reconstruct the flow and how we can do this with our reverse engineering needs, where we want to know what is executed somehow. And there are two levels you can use. The first one is the call trace. So as I mentioned, there are calls that are recorded. If a function is called, that's always recorded, and every branch is recorded. And on the high level side, it's good to start looking at the call trace. So you know at the end what function are really called within. And then if you get a rough idea what is executed, you can look at the assembly stream as well. Then you decode with the focus on the assembly stream. But there's even more. So you can look at mmap events, we will talk a little later, or look at branch events, or look on power events as well. So there's a lot of other things you can do, but for the reverse engineering side, this call trace is a high-level analysis, and second, the assembly stream. These are the two commands you will have in mind and work. How does it look like? So if you take the call trace, what you see there, you see it on the left-hand side, you see in the first row the executable that is executed or was where the recording was done. Then you see the dynamic shared object, the DSO. So if code is executed for an executable, it's not always that it's in the text segment of the executable itself, it's also the libraries, right? If it's called printf, it's executed in the DSO. And this is what you see in the second column. And in the third column here, you see the function that is, if you don't have debug symbols, which is what you normally don't have, you see addresses here. But this is also great because if you have a malware that calls system calls, that calls libc function and things like that. So you get a rough idea what's happening there, and then you need to analyze and focus on the malware. And that's what you see on the right-hand side. So if it's just a call here, it's the main function somewhere. You see it with the red arrows somehow. This is just the main function, the call trace, just one line. But if you use the disassembly trace and encode or decode this way, you see what happens in main. So all the functions, all the instructions that are executed will be seen there, become transparent. And on the left-hand side, what I skipped here was the timing. So also the timing can be in a 2-digit nanoseconds resolution can be shown here. I just skipped this, but this is you remember hopefully the XZ CVE from February. This was discovered because SSH has slowed down somehow. And this was exactly the thing, where does this slows down and where does it block? This can be really analyzed here. This timing behavior, where happens things now. And then just looking at the timing aspects, where are larger deltas, then you know, okay, it's happening here, and then you can focus there. And also the XZ CVC, there are some anti-debugging things. So you cannot look with the GDB what happens there, or you must patch out things or skip instructions somehow, what you regularly did. But this works just by using Intel PT. And you can use this framework to build your own tools somehow. We can talk later afterwards, because you know the instruction pointer and all the instruction are executed. It's really not easy, but to build your own custom tools and to get an idea what instruction or function are called somehow. We can talk offline. I built some custom tooling also there here on this thing. Just get the slides after, and Now some challenges or some other tips. Often you record too much. There are filters. There are hardware filters that are supported by Intel PT. You can start tracing at a particular point. So if you can limit things, you can limit things with Intel PT. You can filter. That's only a particular function. It's a function start and end address somehow. You can hand over this. So you can limit things. You should limit recording because it's getting quite large. This is important. We already saw the PT write instruction. These are important because you can set markers there. If you know something is in this area you want to analyze, just patch out this, write these markers there, and then you have these markers, and then you can analyze the instruction flow really in between. So the markers are really handy. You always find something you can patch out to add these markers. Yes. Then what I already mentioned was the amount of data. I just here for 10 milliseconds, I record Intel PT for all the CPUs here on the larger system. The recording size is 2.7 megabytes file size, but if you decode this, it becomes nearly 1 gigabyte. So really a large one. It's decoding, so you see how good the compression was with the Intel PT packets. But if you decode this, becomes quite huge. So it's good to limit things, to time limit things, what you want to decode. And and sometimes you get overloads because of a lot of data still recorded with Intel PT. You can increase the buffer size for the recording, and there's also a snapshotting mode, so that the recording is always done somehow, but then you send a secure 2 signal to perf, and then it just get the buffer to user space, and you don't experience this overflow thing. So just a little some tips here also. So some limitation it comes to the end is you see a lot, but what it's not visible even to Intel PT is if the instruction is not there regularly and cannot be decoded. So it needs the ELF binary or the ELF object to decode things. If it's a shell code that's loaded from the internet somewhere, it cannot be decoded. If there is using the malware is using some kind of interpreter things, and it cannot be decoded, right? Because it needs a reference point in the ELF object to get from the branch information to decoding information. So this is where it will not work, and it captures not data. So if you debug, you can get all the registers and look at the register. This is not recorded. So you don't get any data that are transferred somehow. For ARM, there are some counterpart, a core-side ETM somehow. And for AMD, there is no counterpart, but you can just execute things on Intel, and then this works somehow. And now we have 4 minutes left for questions.
Thank you. So, okay, we have a question.
Hi. So looking at the limitations, it kind of makes me think like, how well would Intel PT integrate with other RE tools except for perf, maybe with Flash, with IDA Pro or Githra? Because
this is a great question because I really started to integrate things. There is no integration for this. There's a library and a small application, a standalone application provided by Andy Klenn somehow, a standalone tool, but there is currently no integration into the larger reverse engineering tools somehow. So for this, I started to build an own tool to get things done, so really see what is executed, but this is a toy prototype somehow. I think there is a lot of things that can be done in the future, but I am not sure if there's another program. I never see one.
Having challenges with like merging of the static analysis and so on. So
yes. So what I use there is to switch the tools there, and then I get an idea with Intel PT and perf somehow, and then I switch to Redera. This is what I'm using. I'm somehow a VI user, so I'm somehow a Redera 2 user somehow, and then I combine the results of both tools somehow. This is how I work. But I think there's some possibilities and do more with this technique with some high-level reverse engineering tool.
Thank you, because for me, absolutely, this is something new and I never had tried it, but I'll definitely take a look at it.
Yeah. Okay.
Any other questions?
Hi. You mentioned you wrote some scripts.
Yes.
Check. Okay. Sorry. You mentioned, like this one. I'm curious, have you written some scripts to monitor like low-level code, like firmware code or like system management mode code? Because with IPT, the package should be able to capture all of that as well, right? Which would be even invisible to the operating system. I'm just curious if you've explored this space.
No. Just analyze the kernel code, but not below the kernel. Mainly it's user space code, what I analyze.
Mm-hmm. Okay.
I'm doubt that in this ring that the recording is even allowed, but I'm not sure really the firmware stuff.
Okay, thank you.
But it's a great question, but yeah. But normally you have everything happens somehow in user space somehow, and then you limit on user space the malware stuff, right? That's what I focus on.
So any way to detect that something is running with Intel PT?
Sorry?
So let's say if I am a malware, any way for me to know that I'm being instrumented?
Yeah, as I mentioned, this is great for Intel PT, right? So the malware have problem to detect things. The malware do a lot of things to try to detect if it's debugged somehow. Look at a ptrace, call a ptrace system call if there's another one. Open a proc file system and this file system if it's traced somehow. Look if it's a VM executed somehow. This is great because it cannot be detected besides probably some timing aspects, but it's some regular, in the regular area where it's a slowdown of 5% cannot be detected in this way.
Okay, one related question. So Intel also has PIN, which does the instrumentation by your own kind of logic.
Yes.
Any significant differences if you would?
Yeah, it's a complete different stack somehow. The Intel PIN, the Intel PT is really the hardware layer that's recording this, so there's no correlation to Intel PIN in this way. Okay. Really distinct technologies.
Okay, thank you.
Yeah.
All right, thank you for your questions. We are now 1 minute past, so if you have more questions, please catch them in the hall. And give them one more time a big round of applause, and thank you so much.